Now guys, welcome to Teddy Talks. In this video we are going to look at the graphs of motion, and in this video our main focus is displacement time graphs. Now under displacement time graphs we are going to look at 4 scenarios, and the first scenario is when a body is moving with uniform velocity. Now when a body is moving with uniform velocity, the distance increases linearly, such that the graph we get is a straight line. Now, since this is a plot of displacement against time, we have plotted displacement against time. Now, if we happen to calculate the slope of this graph, if we get the slope of this graph, of course, you know our formula of getting the slope is drawing a very big triangle. Now you're seeing that slope is displacement out of time. So the slope we get here becomes our velocity. The slope of this graph is equal to what? Is equal to velocity, i.e. this is displacement out of time, which is equal to velocity. And you really see that if this is displacement out of time, this goes in the units of velocity, therefore it is true, and the slope of our graph is a displacement time graph. Now, the second scenario, let's look at when a body has motion under constant acceleration. What do we mean by constant acceleration? When we say constant acceleration, it means that this body moves with the change in velocity is 0. The moment we hear the word constant acceleration, then that tells you that what? That the change in velocity becomes 0. Now, when we plot displacement against time, maybe this is a reminder, S on our graph stands for displacement. Now, if we draw a tangent, if we happen to draw a tangent to one of these graphs, now the tangent to this graph gives us instantaneous velocity. The velocity at that tangent, we call it instantaneous velocity. This was a curve that was of nature. Now let's look at a body that moves under constant deceleration. Now when a body is moving under constant deceleration, one, this tells you that yes, the speed, the distance being covered is increasing, but as the speed is reducing, then the speed does not also again increase linearly. It begins becoming somehow flat until when the acceleration becomes to 0. Now when the acceleration is 0, what happens is that our graph looks like that. It tends to flatten. So the moment it just becomes a straight line, then it means this is the end of our motion, or the acceleration has become 0. In other words, the body that was moving has stopped moving. Now let's look at motion of a particle projected vertically upwards. Now when a particle is projected vertically upwards, what happens here is that it moves up with increasing distance, and a point is reached when the velocity of this body becomes constant, and then it reaches a point where it begins to come back. Now at the point where it is beginning to come back, this point we call it maximum height. We call this point what? We call it maximum height. Now why do we call it maximum height? It is the highest point reached by this particle, and the time taken to move from the point of projection up to the same horizontal point at the same level point of projection is called time of flight. Now, we see that t is time taken to reach maximum height. Is the time taken to reach maximum height, and 2t is called the time of flight. It is called what? It is the time of flight. And when you observe this graph of ours, it shows you that the time taken to move from the point of a projection up to this maximum height, and then the time taken to move from the maximum height up to the same horizontal level as the point of projection is twice the time taken to reach here. I mean, the whole time for the whole journey is twice the time taken to reach maximum height. And what else can we conclude from this? We can as well conclude that this tells us that the path described by a particle that is projected upwards is symmetric. That's what we can conclude. So these are the displacement time graphs under the 4 different cases. In our next video, we shall be looking at velocity time graphs.